6-2, solving systems using substitution. Our objective, to solve systems of equations using substitution. You can model fair trades with linear systems. You can solve linear systems by solving one of the equations for one of the variables, then substitute the expression for the variable into the other equation. This is called substitution method. Essential understanding. Systems of equations can be solved in more than one way. When a system has at least one equation that can be solved quickly for a variable, the system can be solved efficiently using substitution. 1. Using substitution. What is the solution of the system? Using substitution. So again, we're looking to see where these two equations cross. And so we're going to use substitution. This equation, y is equal to 3x, makes it real easy. All we have to do is take the 3x and substitute into the other equation. So I'm taking the equation x plus y equals negative 32. I'm taking the other equation, y is equal to 3x, taking out the y and putting in the 3x. Once we substituted in the 3x for y, we can combine our like terms. X plus 3x is 4x, and we could start doing our algebra. With our algebra, we divide both sides by 4 and get x is equal to negative 8. Now we know where our x is in the ordered pair that we're looking for. So we take our negative x that we found and we substitute it in to the original equation, multiply by 3, so y is negative 24. So now we have our ordered pair of negative 8 and negative 24. Just like graphing, we take our ordered pair and we substitute it back into both equations. So we have negative 24 substituted in for y is equal to 3 times negative 8, which is negative 4. So it worked with the equation y is equal to 3x. And our other equation is x plus y equals negative 32. So negative 8 plus negative 24 equals negative 32. So we have negative 32 coming down on the other side. So this is equal, so it did work for both equations. In problem 2, to use substitution to solve a system of equations, one of the equations must be solved for a variable. So you see in these two equations they're giving us in problem 2, neither one of them says y is equal to or x is equal to. So we need to solve for y in one of them. So I see a real simple one would be right here where it already says y. So I'm going to add 2x to both sides of the equation. So you can see we have negative 2x, so we're adding 2x to both sides of the equation. Y is by itself equals 2x minus 3. So now we can use 2x minus 3 and substitute it in to the other equation in place of y. You can see here's our y that we solved for, and we need to substitute it in right here. We're going to pull out this y and we're going to put in 2x minus 3. So this is what it looks like. You can see 3 needs to get distributed, and then we'll combine like terms. So 3 times 2 is 6, 3 times 3 is 9. We're subtracting, so that comes down. Now we got to combine our like terms and we get 10x, but we need to get rid of this negative 9. So we add 9 to both sides and get 23. So we divide by 10, and so x is 2.3. Now that we know our x, we need to find what our y is. So x is 2 3/10. So I take my other equation and I substitute in, take out this x and substitute in the 2 3/10, and then solve it for y. So here I have to multiply, so I get -4 6/10, and I add it to both sides of the equation, and I end up with y is equal to 1 6/10. So my solution is when x is 2 3/10, y is 1 6/10. So this is where what works for both equations. This is where they cross. 3. Using systems of equations. At the snack bar. The snack bar sells 2 sizes of snack packs. The large snack pack is $5. The small snack pack is $3. In one day, the snack bar sold 60 snack packs for a total of $220. How many snack packs did the snack bar sell? So we need to declare what our x and our y is. So we're going to write a system of equations. We're going to let x be the large $5 snack packs, and we're going to let y be the number of small $3 snack packs. So once we declare that, we can write our equations. So the first one is x plus y equals 60, because that's the total number of snack packs that we have. Our second equation is 5x, because the larger backpack is $5, plus 3y, so it's $3 for the smaller one. And the total amount of money is $220. So you can see the cost goes with the total cost. And then for the number of snack packs, it's just the x, the variables, the x plus the y. So if you can pay attention to the pattern of how they're matching up, it's easier to write the equations. So we're going to use the first equation to solve for y. So we're going to subtract x from both sides. So we have y is equal to 60 minus x. And we need to substitute this into the other equation. And so we're pulling out y and substituting in 60 minus x. So you see order of operations, we need to distribute and then combine like terms. So there we distributed 3 times 60 is 180. 3 times negative x is negative 3x. So we combine our like terms. 5x minus 3x is 2x, but we also need to get rid of this 180. It's a plus 180, so we subtract 180 from both sides to get 40, but we're still not done. We need to divide by 2. So x is equal to 20. So we know that x is 20, but we still need to find what our y is. So x is equal to 20. So we substitute this into one of the equations, and we have 20 plus y equals 60. So we can see y is equal to 40. So the system's solution is 20, 40. The snacks bar sold 40 small snack packs. Problem 4. Systems with infinity many solutions or no solution. How many solutions does each system have? So here's our 2 equations that we're trying to find a system of solutions. So we substitute in the negative 2y plus 4 into the x of the other equation. So here it is getting substituted in. We distribute, and we notice we have negative 7y and 7y. And we end up with just 14 on the side, and we have 14 equals 14. When you run into that, the system has infinite many solutions. On part B, we have two equations again that we have to substitute in for, and this one's already solved for y. So we're going to take this y and substitute it in for y in this equation. So here's my y that's coming out, and in comes 3x minus 11. And we notice we have 3x plus 3x. So there's 0, and negative 11 is left, and it says equal to negative 13. And that is not true. Notice this is not a check here. This is saying, no, that did not work. The system has no solution. There is nowhere that these two cross.